We're given a Cobb-Douglas production function P of L comma K. We want to find the marginal productivity of labor and the marginal productivity of capital functions, which would be the partial derivative with respect to L and the partial derivative with respect to K. Before we do this though, let's talk more about the Cobb-Douglas production function. In economics, the Cobb-Douglas production function is a form of the production function often used to represent the relationship between physical capital and labor and the amount of output that can be produced by those inputs. So this is the form of the Cobb-Douglas production function, where P is the total production, L is the labor input, K is the capital input, A is the total factor productivity, and notice alpha and beta, the exponents, are the output elasticity of labor and the output elasticity of capital. So going back to our example, we'll now find the marginal productivity of labor function by determining the partial derivative with respect to L. So to do this, we'll differentiate with respect to L, treating K as a constant. So we'd have 12 times, if we differentiate with respect to L, we would multiply by 0.7. Then we'd have L raised to the power of 0.7 minus 1, that's negative 0.3, and we're treating K as a constant. Now let's go ahead and simplify this and write this only using positive exponents. So 12 times 0.7 is 8.4, so we'd have 8.4. K has a positive exponent, so that would be in the numerator, so K to the 0.3. And because L has a negative exponent, we'll move it down to the denominator, which would change the sign of the exponent. So we'd have L to the positive 0.3 in the denominator. So this is the marginal productivity of labor function. And now we'll find the partial derivative with respect to K, which would be the marginal productivity of capital function. So we differentiate with respect to K, now treating L as a constant. So we'd have 12, then we'd multiply by the exponent on K, which would be 0.3. L will stay the same, L to the 0.7, and then for the exponent on K, we would subtract 1. 0.3 minus 1 is negative 0.7. Let's go ahead and simplify. 12 times 0.3 is 3.6. L has a positive exponent. And the denominator would be K raised to the power of 0.7. Now that we have our two functions, we're asked to evaluate them when L equals 400 and K equals 1000. After we do this, we'll explain what this means. So the partial with respect to L, notice how the coordinates are L comma K, so it'd be 400 comma 1000. Again, where L equals 400 and K equals 1000. So for the partial with respect to L, we would have 8.4 times K, or 1000, raised to the power of 0.3, divided by L, or 400, to the 0.3. We'll evaluate this in just a moment. Let's go ahead and set up the partial with respect to K at the same point. So we'd have 3.6 times L, or 400, raised to the power of 0.7, divided by K, or 1000, raised to the power of 0.7. Now we'll evaluate these on the calculator. So first we have in the numerator 8.4, and then times 1000. This is raised to the power of 0.3. Right arrow, close parenthesis, that's the numerator, divided by 400, raised to the power of 0.3. Enter. If we round to 3 decimal places, this will be approximately 11.058. This is the change in production with respect to labor at this point. And next we have, and now for the partial with respect to K, we have in the numerator 3.6 times 400 raised to the power of 0.7. Right arrow, close parenthesis, so there's the numerator, divided by 1000 raised to the power of 0.7. Enter. To 3 decimal places, we'd have approximately 1.896. Now let's emphasize what these two values represent. The value from the partial with respect to L, which we found here, is the additional output that results from employing an additional unit of labor when L equals 400 and K equals 1000. So we can say at this point production is increasing at approximately 11 units per worker. And then for the partial with respect to K, this represents the additional output resulting from the use of an additional unit of capital, again when L equals 400 and K equals 1000. So the units on this value would be units of production per, let's say, dollar. I hope you found this helpful.